All right, great.
Whenever you want.
Right, whatever. Don't worry. Okay, so I think we can start and start the recording here. So before we go on, so what the plan is for today is to finish the overview of C++, so that you all have sort of a base level of what you should know about this language that we're using in the class. And then I'll present you with a homework where you can try out some of these things. But before we do that, are there any questions about last time, or what we covered last time? Don't feel shy. I mean, if there's something that isn't quite clear right away, it's easier just to ask. Okay, we're not. You can go over this more carefully if you need to. Okay, so we ended last time with functions, and I think this is the last one that I showed, where I had a function prototype that declared what the function looks like, so I can use it in main, and then I defined the function. That is to say, I said what it actually is to do after that, and that's the purpose of having this. And this last function definition here is in the same file, but it doesn't have to be. It could be in a separate file, and so that way we could do something like modular programming, about which we will hear more next week on Tuesday. But this kind of separation is what makes that possible. Anyway, we're focusing mostly on syntax and how to do things in C++ these lectures. So there's one thing that especially people that are coming from a different language like Python or Fortran, a few things that one has to be aware of when using functions, particularly when it pertains to arguments. And that's the difference between passing an argument as what is called by value or by reference. And this is easier demonstrated by an example. So here's a little example. The first function, inc, is trying to increase the value of the integer that it gives. So it's not supposed to return anything. It just needs to increment that same variable there. And if it doesn't return anything, you can have it have the return time void. That's what this void means here. So it just means this doesn't return anything. It just does something with the arguments. So I is I plus 1 will definitely increase the argument by 1. And then that function gets called in main. So I define another variable called j. I set it to 10. I call the function inc j, and then I return j. Remember, in main, we can return a value, and it becomes the exit code. This is just a fancy way of me not having to write anything to screen. So I could compile it. Compile line is a little longer than fitted here, so this should be one line. And run it. And then to get this value out, remember we had this break echo dollar question mark, and I get 10. Now that should be a little bit surprising because we're supposed to be increasing this 10 by 1, and we should have been getting 11. So let's see why. So initially, in this first line, j is set to 10. And then this j is passed to the inc function. And so what happens is this value of j is copied into a new variable called I. That's kind of why this looks like a variable declaration. It's a new variable called int. And so what this actually does is it copies the value of j into I. I is a new variable inside the function. And then that variable inside the function surely gets increased by 1. But since it was a copy, it was not the original variable. With j, nothing has happened. And that's why when we return j, we just get 10 because j hasn't been. So this is called passing by value. It's the default way arguments are passed in C and C++. And this is different from, say, Python or Fortran. And so obviously we'll want to go, we're on the way to get around this, and there's a second way to pass arguments, but this is what's happening. So you don't pass the variable, you pass a copy of it by default. You pass the value, not the variable. So we can try doing this by reference. By reference really means I pass the variable, and when I change something in the variable, that reflects to the original variable as well. So all I had to do was add this little ampersand. I don't know if you noticed that, but this little ampersand is here. And that signifies that this is a pass by reference. And when I compile again, now the output is 11. So what happens here is that j, being 10, is passed to inc, where it's the same variable, it just gets a new name. So another way of thinking about these passes by reference is that I just rename this j to be called I inside the function. That's all that happens. And so I increase I by 1, but I is the same thing as j, just another name for it. So the original variable also reflects. So when you pass a variable to a function and you want it to be able to change, you add the ampersand. If you don't want it to change, you don't do that, and then you get a copy. There's cases where making a copy might be expensive and you do the ampersand just for speed, but that's just a second thought. So as a language, you should think of, do I want this value or do I want the actual variable? All right? I added a list of operators in C++, just so you know what's there. The things on the left here, or on the top left here, are pretty, most of them are actually self-explanatory. You can add, subtract, multiply, and divide. If you want to take the modulus, so the remainder of A and B, so that's this percent sign, so 15% 10 would be 5, just a remainder of 5. There's logic, so things are equal. You can say A equals equals. Be aware of this. This double sign is important to test for equality. If you do a single equal sign, it means that you're equating B to A, so A gets the value of B, which is not what you want if you want to test if they're equal, because you've just made them equal, which has side effects. If you don't want it to be equal, not equals, you can also use the keywords not. If you want to test for two things, you can say and or. And is double ampersand, and or is double bars. But in C++, you're also allowed to just use not and or if you find this more easy to read. But you'll get some code. You'll see some code where they use these double ampersand. So you should. Assignment we also briefly saw how you can add a value to something. So plus equals. So it's an assignment. So an addition plus an assignment essentially, and they come in all the flavors of subtracting, multiplying, dividing. And you can also increase the value by 1. This is so this plus plus means the value of A gets increased by 1. This same operator is where C++ gets its name because it's supposed to be C, but then better, so C++, it's increased by 1. Nobody is there to put a C minus minus out there. So that minus minus decreases the value. We'll see where these things come in handy, but just so you know. So with those operators, I want to ask a question. You know the answer if you download the slides, but what's 1 divided by 4?
Sure.
Yeah, you looked at the slides, didn't you?
No, I can proceed.
Oh, you took C. Okay. Who was surprised by that? Just nobody. Oh, I gotta go through this very quickly. So the point here is that C++ is a heavily typed language, right? Everything has a type. And so that's true for literal expressions too. So 1 has a type, and 4 has a type, and their types are integers because there's no decimal point. And so if I take the division of 2 integers, the result should be yet another integer. And the closest integer to what 1/4 would be is 0. So basically rounds down by default if you do integer division. It's something to be aware of because it's something that you can bite you when you don't. So 1/4 is 0 in integer arithmetic. Now, typically that's not what we want, so we need a way to make those integers into doubles. Well, we could do that by adding a decimal point. We can also do it by explicitly converting them from integers to floating points. So here's one way you would do that. So float is a type, but you can also treat it as a function, and then it converts whatever you give to it into a float, if that's at all possible. Sometimes this is not possible, and the compiler will tell you you can convert a string to an integer. It doesn't make much sense. Actually, it does make sense, but the compiler doesn't know how to do it. So float A over float B makes both these integers into floats, or just their values, and then the division becomes floating point, and it becomes 0.25 as it should. Okay. Yeah. Yeah. Okay, so the order of arguments doesn't matter as long as the name of the application follows the -o. So I can reverse the order of the .cc and the -o 1/4, but I have to treat this as sort of a single clause. Okay. Now some things get casted automatically, just so you know. So I could write 1.0/4, and then it actually says, okay, you've got an integer and a float, but in this case, I know what you mean. So I'm just going to make that 4 into a float for you. This can, however, be, so this happens, and this one is good. It also happens in sort of a bad way, where you could pass a floating point to a function that expects an integer, and now it rounds it down. This is very annoying when you don't expect it. So if you were careful enough to choose the right types for your arguments, you would have made this into a float. But if you didn't know it, then you can certainly get unexpected results. So you can both upcast and downcast. Okay, so that's just some peculiarities of those operators. But now a little bit more to the point of scientific computing are loops. So we'll talk about loops for a second. Loops are anything that you do more than once. And it's very common because we either have a big grid that we want to do something for each point, or we have a whole data set that we have to loop through. If you only had one thing to do, we'd probably not even use the computer, or we just use a calculator, right? So loops are very, very essential. And this is how you do them in C++. There's essentially 3 ways, but I'm only going to show you 2. Because the third one requires some C++11 specific stuff. So the first form is called for. Second is while. While is easier. Whatever is in between these braces, these statements are done while this condition is true. So you could check if a variable is 0 or 1, or whether file is closed or at its end. So while that happens, this is done. So it's done again and again until the condition is false. For for, it actually is just to hit the same idea. There are 3 parts to the for statement. And then there's the block. So the block again gets done again and again. You initialize something, then there's the condition, and then there's an increment. And show an example because it's easier to see this by example. So the initialization could be setting a variable I to 1. And so we declare the variable I and set it to 1 right away. That's an initialization. I want that to be the first case. Then I want to do everything inside its code block until I is 10, or actually including 10. That makes sense. But then I have to do this increment clause where I say what happens to each I after a loop is done. It's a very manual way. I have to increase I by hand. This is very different from other programming languages where this increment will be done for you. Not in C or C++, you have to do that by hand. So 3 parts: initial parts, the condition, and the increment. Another thing that I did here, and I only do this to confuse you and prepare you for confusing code, there are no braces here that surround this code block. And this happens quite frequently. If there's no braces, the actual code block is just the first statement that you have. So just only this statement is done again and again and again. This is not part of the for loop. So I'm printing out I, and I'm ending the line only once. So while the general syntax has these curly braces, a single statement counts as a full block. This is why you should be very careful to indent your code properly, so that you can actually sort of visually see that this is the only statement that is going to happen in the loop. If you indented this further, it wouldn't suddenly become part of the loop. This is not Python, but it would look to you at first glance that it should be done, and so that's not a good. So here's the count. This counts from 1 to 10, and this is how you do counting in C++. Slightly elaborate, but very general. So because this increment, I could increment it by 2 if I wanted. I could increment it by multiplying by 2 if I need to go over powers of 2, say. So it's a more general way. So it can be powerful. Just for the simple cases, you've got some more typing to do. Yeah, sure. Excellent. Good point. So if a function is to return something and there's no return statement, that's a big no-no. The standard says no, except for the main function. It'll say, well, okay. So it's not very good form. I should have put a return 0 or something, because so many people leave out a return in main, they put in the standard set. If you don't have a return statement in your main, it returns 0. It would still work, but it would tell the operating system that something might have gone wrong. So if this was somehow embedded into some other application that tests whether this was correct, if it returned 1,000,000, it would say, hey, there's an error, I might as well stop. So and eventually you're going to use some sort of pipeline where one function or one program might be called in a script by another program, and so keep returning 0 if you want that. Okay, so the next topic is pointers, which is a little bit complex. Can be a little bit complex, but not if you keep it simple. So we're going to try and keep it as simple as possible, but we'll need some pointers when we're dealing with arrays, and so I have no choice but expose you to this a little bit. But in its essence, pointers are just memory addresses. So remember, a variable has a name, and then it lives somewhere in memory. Well, that memory is basically one linear space of bytes. So rather than using the name of the variable, I could just say, well, it's there in memory at spot 1,305,000,000, right? That's what you're doing with a pointer. You're basically saying it's at that spot. It's just an address, memory address of the variable. And sometimes that can be useful, because at times I don't want to create a new variable. I just want to say, well, the variable that exists somewhere else, I want to do something with it. So I want to point to that variable. So that's kind of what you use pointers for, to point at other variables. Now, the syntax of it is a little bit terse. So as with everything in C++, this is a type language. There is a pointer type. And for every kind of variable you have, an int, a float, there is a pointer type corresponding to that by saying that same type star. So there's an int star, a float star. And that means that you, in theory, could only point to a float with a float star, and it would know what is in that address. This matters because floats, double precisions, integers, characters, they all take different numbers of bytes. So it kind of helps to know what it is that you're pointing at. It's useful in arrays, linked lists, binary trees. We'll see it come by a few times. And then there's a special pointer that, as you point out, sometimes you have a pointer that doesn't need to point at anything, or does not yet point at anything, right? So, and to denote that, there's this null pointer, which is a keyword in C++11 at least, that says, okay, this isn't pointing anywhere. Sure.
This isn't addressing.
Well, it might just not have been initialized yet, right? So if you didn't initialize that pointer to anything, it would point at an arbitrary position, and you'd have no way to test that it's not initialized. So whenever you have a pointer, you should initialize it with null pointer or something real right away. Because that way, another part of the code could test whether this is pointing anywhere or not. If it's a value, if it is 1,000,001,000, the code can't know if that's a real address or was just something uninitialized. If I started at that null pointer, you can do that test. So it's a good way of initializing things and being able to write code that can check for consistency. So just for completeness, this is the syntax. So whenever you have a type, a pointer type, you have type star and then the name. So you can think of type star as a type, but the way the parser of C++ works is kind of associates this star with the name. Don't ask me why. This is historical. This is what it does. So you'll often find type star name. Oops. And it means name is a pointer to something that is of type. If I want to assign it, I have to say I want name to point at the address of a particular type, a particular variable. I use the ampersand operator. So the ampersand is basically the address of. If there's a variable x and I say ampersand x, I get the memory address of that x. And then if I want to get, rather than the address, whatever is stored in the address, I have to use this star once more. It's called dereferencing, but basically means get whatever in that address. So if I stored 2 in that variable, I had a pointer that points at that variable, and I said, well, star that pointer, I'll get 2 back. Okay, so just taking addresses and taking things from the address. That's the main purpose of pointers. I have a convoluted example just to, not to mess with your heads, but just to show you what happens with pointers in detail. So the idea here is that the first line just initializes 2 regular variables, a and b, and a is initialized to 7 and b to 5. Then I initialize a pointer to an int. So this is an int star, that's the type of pointer, and I initialize that to the address of a. So as I said, it's a good idea to initialize pointers right away, either to null pointers, so that you know it's not actually initialized, or to an address, and this takes the address of a. So a lives somewhere in memory, ampersand a is that memory location that I've stored in pointer. Now I'm changing a to 13 here. And then I want to store in b that which is stored at memory address PTR. So at memory address PTR, there's an integer. I know that because pointer is of pointer type int star. And with the star, I say get that integer, and I put it in b. So since I've put 13 in a, and a is what lives that pointer, b gets that 13 as well. And so when I print it out, I get 13. Okay? Not saying this is sensible at this point, but this is the mechanism of pointers. And so if you kind of understand this, when you see pointers used in a sensible way, you'll go, okay, I kind of know what's going on. Yeah. Don't worry about this. This is really more. Yeah. Yeah. This is just to introduce the syntax and have one place where all of. So lectures 1 and 2 are combined lecture set for a reason. They can be your reference after the fact too. To sort of go, okay, what was the syntax again? You don't have to look through all the different lectures. This is it. So this brings me to something related to pointers called arrays. Arrays are repetitions, not repetitions, are the same type of variable, but then in a line, right? So you can have 10 integers at a line. I have an array of 10 integers. There's a very simple way to use arrays in C++. You just type the name, type the type, type the name. That would create, if I only had that, a variable of type with name. And I can have a certain number of them in square brackets. And that's all. That defines an array. And then if I want to get a particular value, say the first value, I say name, and then in between square parentheses, I give the index that I want. Now, you should know that C and C++ arrays are zero-based. So the first element of an array has index 0. Just an example might be easier to see. So my first line in main there creates an array of 6 integers. And with this curly braces syntax, I can actually initialize it right away, 2, 3, 4, 6, 8, 2. So this is an array of 6 integers. I could sum them up. That's what the next part does. By going over the loop I from 0 to just below 6, so 0, 1, 2, 3, 4, 5, because the indices of these numbers are 0, 1, 2, 3, 4, 5. There's no element 6, because although there are 6 elements, the 6th element is index 5. I'm summing them up, so I'm using the plus equals. I'm using these square brackets to get the ith element of the array, and then I print out the sum, and it gets 25. Okay, that seems fairly straightforward, right? An array, more than one, square brackets, except instead of maybe parentheses if you're coming from a fortran, but other than that, seems good. And then I have this big bad sign. So this is an early warning that you won't get in other C++ introductions. This is why this is not really a programming course. These are called automatic arrays. In other words, the compiler is doing everything for you, from finding a spot in memory for these 6 integers to initializing them. And this is bad because, unfortunately, there are limits to how big your array can be if you do this, that you have very little control over until you become a Linux expert. So in the standard, which actually you have to go back to the C standard to know what the real standard is, that says that this will work, will only be guaranteed to work if your array is no more than 64 kilobytes, which is a puny array in modern standard, right? So for this, yes, 6 integers will work just fine. But you're going to have arrays that have 1 billion elements or 1 million doubles, and your program will not work. And it will not work in the sense that it doesn't compile. This is the real sticking point. It will not work in the sense that it will compile. You try to run it, and you get what's called a segmentation fault. And a segmentation fault is saying something's wrong with your memory. But it will not tell you what. It will not tell you what. And so the trouble is, you can run out of this. So what happens in practice, forget about the standard, is that the operating system sets a certain amount of memory aside for these sort of automatic arrays. And when you're done with that memory, too bad, segmentation faults. It won't tell you which array is too big or not. So the best thing to do is not to use these automatic arrays at all, if you're going to have anything sizable. Instead, you'll use dynamically allocated arrays. Unfortunately, there's a whole construct for that in C++. So what we're going to do instead of these automatic arrays, and we'll try and do this throughout all of the course, is to do things a little bit more by hand. We'll have a pointer, will be called name, of a certain type. The type is what type of array elements I want. And then I can create an array by saying this new type. So new type and then square brackets number. Does the same thing. It creates number elements somewhere in memory. Might initialize them depending on the type, but in standard it does not. And then returns where that array starts. So I have, say, 10 elements, and it will return the pointer to the first. And I can start using them because I now have the pointer. And then I can delete it specifically as well by doing this delete statement. So this is kind of what it looks like improved. So here's me creating a new array of 6 integers. And then I'm storing the address of the first element in A. But A, in all other respects, just acts like this array that we had before. I can do A square bracket 0, 1, 2, 3, and I can set the elements. So it's really just a way of defining an array, but storing where it starts in a pointer. This is what happens with dynamic memory allocation. The rest is all the same. I create the sums, I write out the sum, and then at the end, I can say, well, I don't need that piece of memory anymore. Let me delete it. And then it works the same way, but it does this dynamic memory allocation. The nice thing is this will still work when I have a million elements. So this scales. This prevents you from cases where your program worked just fine, your test case of 10 elements, now you take your real data and it's segmentation faults. Don't want that. Okay. One thing that I should also stress is that this delete statement might seem a little bit unnecessary because after all, the program finishes and will actually delete this thing for you. But it's a good practice to give back any memory that you're not using anymore. Because if you don't, your program runs for a while and keeps asking for new and new arrays, it will run out of memory. You'll have what's called a memory leak. So anything you allocate dynamically, you should deallocate yourself. If you allocate it yourself, you should deallocate yourself. This is why this is not an automatic array. Automatic arrays do that for you, but then they have all these side effects that you don't want. So this is how we are going to use arrays, new and bleak. It's the same thing as malloc. That's right. The only thing that it does in addition is if you have some complicated type that initializes itself in a special way, that initialization will be called. It's called a constructor, and we'll see that when we're talking about object-oriented programming. And malloc doesn't call any function for you. It just gives you the block. Yeah, right. So, but 6 can be a variable. So you could have input that says, so it doesn't have to be a hard-coded value. It cannot be blank, no. And some compilers even have trouble with doing an array that is 0 size. Some don't. But yeah. One more example. I'm going to go over. Oh no, this is what I have to point out. Sorry, this is what it prints out. So I have an array, and there's a function that prints the array. And the only point about this is that since with dynamic arrays, you're just getting back the pointer to the first element, it's up to you to remember how many elements there really were. So here in main, this was coded in a variable called n, fine. But then if I call the function, that function might not know that, or would not know the number of elements in the array unless I pass that as an argument. So typically when you're passing in a dynamically allocated array to a function, since it's only a pointer to the first element, I also have to say how many points there are in that, so that I can use that and do the proper loops. So arrays in C++, when you do them dynamically, are a pointer and a integer that stores how many elements there are, and you have to keep track of them both. That seems like a lot of trouble. Why don't we just use the automatic arrays until we are at a bigger size? But in fact, the same happens with automatic arrays if you pass them to a function. They sort of get converted to the same kind of, I'm just a pointer, I don't know how big they are. So whenever you pass an array, you're going to pass how big it is. This new and delete, I just want to mention, you can also do on single variables. There's less use of this, but you can create a single double without square brackets and delete it without it, and you just get one element. It's mildly silly unless you have a really big type that needs allocation. So in this context, just as FYI. This is a little late, but we mentioned conditionals. So if statements, they exist in C++. There's two parts, or one part, depending on whether you have an else statement. So there's if. This has to be between braces or between parentheses, and then a block that happens when that's true, and a block that can happen when it's else. You can leave out the else if you want to. How it looks. So what I'm doing here is kind of checking whether this new was correct. If it doesn't, two things can happen. The program can crash, or it can return a null pointer. And it kind of depends on the compiler and the flags that you give it. Most modern compilers won't even make it to this point, but that's fine. But if they do, they could return a null pointer. And this is actually a typo. This should have said null pointer rather than 0. So it's an if statement that checks if this memory allocation was valid. Okay, so that's basically arrays and if statements. Questions about that? And we'll move on to another keyword that you'll see a lot in C++, const. We're going to use this very lightly, and I don't even mind if you don't use it at all, to be honest, for the homework. It's something you should know about because you're going to see it in code. Const changes the type, any type, into being a constant. And so if I say const int array and I assign it a value, I am not allowed to assign array size to anything else. So it can be very useful as a safeguard. Something is a parameter, this should never change. We put constants in front of it so I can't accidentally use that variable in a loop or change it and get side effects that I don't want. It's also useful if you want to pass things by reference, but not change them. So you can make arguments in a function also constant, and then you can't accidentally change them in the function. I should warn you, const is contagious. Once you put const in your code, things that are const and are passed to something that doesn't expect the const stuff will give you an error. So things have to be const correct, as people say. That's why you should be sparing, usually sparingly, especially if you're starting with a new code, until you're really comfortable with what's done. But for constants, it's a useful little thing. Object-oriented programming, and this is just about the syntax of using them, is something that's kind of central to C++. In essence, it's what prompted the creation of C++ out of C to add object-oriented programming. And what is object-oriented programming? So object-oriented programming merges the idea of data and functions. So without object-oriented programming, you have functions, and you have data, and data gets passed into functions, and then the function can act on the data, but there's nothing tying the two together. Even though there might be functions that are really designed to work on a specific type of data, there's nothing that really forces that or makes that transparent, that's how it's supposed to work. And so object-oriented programming takes the opposite approach and binds these two together. So if you have a bit of data and there's functions that really work only on that data and belong sort of to the idea of that data, you treat that data as an object that can act on itself with the data that it contains. That's the idea. But really you're just bundling functions and data. Another thing that's nice about object-oriented programming is that you can have different objects that are implemented very differently under the hood, have a very similar way of working with them. Think of our pointers and our arrays that both got their elements by using square braces, although one was a pointer and the other was an array. That kind of similar interface to two things that are really fundamentally different can be very useful. You can hide how a certain object is implemented and only make sort of the interface visible to the outside. This can be very nice. Classes belong in the same idea of object-oriented programming, but the idea is fairly simple. An object is a variable that exists, a class is a type of object. So it's just a type of object. And so just as you would define a variable by saying its type and then its name, for objects you would say the class name rather than the type name, and then the name you want your object to have. That can be enough, but then often there's additional arguments to create this object. So objects are supposed to be more complex than, say, an integer or a float. You could have, in principle, an object that is an array. And then you might want to have as arguments how long that array is supposed to be. So those arguments go into these parentheses. And it kind of looks a little like a function call, which is very unfortunate, but it's still, that's how it goes. And then once you have this object, how do you use it? And that is, there's this dot notation. So once you have an object, it might contain data in it. You get it with dots. So object.field is a field contains an object. And then functions that are bound together to this object are done in a similar way, object.method, and they can give some arguments. So a little example here. Strings are objects. So remember, we mentioned that there are strings in C++, and they are preferable on just doing bare char stars. I mentioned this before you knew that a char star is apparently a pointer to a character. And so since it doesn't know its length, this makes it very awkward to work with strings. It's not impossible. It's actually very doable, but it's complicated. So here's an example of where I define a string S. Its class type is std : string. This is defined in this header file string, and I initialize it with hello. So what that means is indeed I put hello in that string. And then I can get things out of that string, like its size. Size is a method that belongs to it, so I have s.size, and I just call it. And so I don't have to give s as an argument additionally in this, because it already is the method that is bound to that object. So it will fetch its own length. Another example is the following. This creates a pair of an integer and a float. We'll see a little bit about the syntax later, but that's, and then I can get the first element out and the second element out just by dot first. So these aren't functions. These are just elements within that, that particular pair. Okay. This is going fast. I realize that. A lot of these things you're not going to use until later, but this is an overview. Okay. And then I must mention this because I gave you this example with these funny square braces. So let's talk about that for a second. So there's this nice class called pair. They can pair any two types. This can be useful sometimes if you want a function to return two things, say an integer and a float. But in C++, there's only one return type. You can only return an int or a float, unless you might return a pair. So having a pair can be useful, but you might want to pair anything, an integer and a float, a string and an integer, two integers, three floats, well, two floats, it's a pair. So the actual pair class is a whole bunch of possible pairs of any possible type. That's what this notation means. It is kind of a argument. These these angular brackets are an argument to this class, saying this is a class for these particular types. It's a specialization of the general pair class to having an integer and a float. And that is called a template. So there's a template in this utility header file or library that becomes a real thing when you say, okay, I want it for the int and the float. Okay. So this can also be used for functions. So you could have a function that works for an integer and a double, and they're exactly the same. This squares x. Without templates, I need two functions because the return type and the argument types have to be specified. They have to be ints. They have to be specific types. I can't say this is anything. I can do this in Python. I cannot do this in C or C++. So I can do two functions. I could do that. That's fine. But then for every time I have a new type that can be squared, I have to write yet another function. And it gets tedious. I get code duplication. And so this is kind of why you would use templates. You write it once with something that has a generic placeholder type. And the only thing that the compiler has to know is this is a placeholder, and that's what this template type name type does. So it's nice that you can do this. We won't ask you to do it yourself unless you really want to. But I want you to know that this is a feature of the language, and that's what these funny angular brackets mean. So I can pick out a specific function by specifying the type, or I can have the compiler figure out that this is an integer and deduce things. The same with class types, and we just saw that. So there was the pair. We saw a template class pair. There's a template class called complex. Can have complex numbers of any type. Obviously, beyond float and double, and maybe long double, there's not much point, but they exist. You can have a vector, which is kind of like an array. In two classes, we'll explain why vector isn't the most ideal array to use in scientific computing, but it is an array. And again, you can have an array of any type. Okay? So put this in the back of your head. Don't think about it too much. There's some things with templates, and they have angular brackets. And then finally, libraries. We mentioned last time, libraries are what gives most of the functionality to this language. Some are standard, like input-output. Some are not standard, like when we're doing MPI, which is a way of parallel programming. You have to link this in specific. If it's standard, the compiler knows where everything is. If it's not standard, you have to link in the library with a -L arguments. So we'll focus on common languages. We'll look at libraries more detail in the second part. Strings, input-output, files, containers like vectors and lists and maps. We'll look at that later. Math, all kinds of libraries are there. And what you really just need is to find the right header file that has this. You can Google yourself where strings are, where files is. The only thing I do want to mention very, very quickly is streams. We saw output with these funny streaming operators. We saw cout, and so that's how you write to screen. There's also a way to read from keyboard that's cin, console in. And then there's a separate stream, as it's called, for error messages. They will go to the console by default anyway. But by having them in different streams, you can have the calling program, like your shell, bash, or the Linux terminal, write the error message to one file and the output to another file. So that might be useful if if you want to separate errors from output. So these are in IOStream. Example, we saw this. But this reads in, what you didn't see is reading in a variable. So we just read it in integer, right? Very nice. I have a variable, I just read it in from the And then file, IO goes similarly. This is an F stream. So I can either read or write a file. Here I'm writing a file. I'm creating an output file stream called fout. And this is an object. So I initialize this with the name of the file, and it opens it for me. It's kind of nice. And so this is one of the reasons why I wanted you to see the object-oriented syntax. So this is all that happens. I have a variable. It's an off stream. I don't have to know exactly what an off stream is, whether it has integers in it or not. It's a file, and I can stream things in it with this streaming operator. I can write an X to it. I can write a space to it, another Y. I can write the end of line. And then the only thing I have to be careful about with files is to be sure to close them. We'll have some file IO specific classes too, but if I don't close them, I run the risk of this stuff actually not being written to disk before the program ends. So this is how you would write it. It's very similar to the standard cout. And this is how you would read it. So rather than using an off stream, you would use an if stream, input file stream. You create two variables and you just read, oh, wait, this should not have twos. It's funny. Okay, these two should not have been there. I'm not quite sure where they. So you read in the two existing variables. You close the file and you can now use those variables. Those reading in and writing out of files. Very basic. Yes, so these are text files. The standard way of doing output in C++ is in text. It will be plain text. There won't be a doc. There won't be an Excel sheet, just text. Okay. There's reasons not to use text at times, which we'll get into in detail. But just think about it. If there's a better way to store your billion double precision files than text, then why wouldn't you? Because you're not going to look at your billion double numbers. So, but these are text. Okay, so that's kind of the overview. There's a few things I went very quickly over. If it went too quick, it's probably not particularly important right now, and we'll go into detail later. But ask questions if you want. And courses at scinet.utoronto.ca is, as is on the slides, is the way to go. So there's a first assignment. They'll basically, for the people that know C++, it's going to be quick. For people that don't, this kind of gets you up to speed. So there's three parts to this first assignment. The first part is to start the process to get a Scinet account. Who here has a Scinet account or has started asking their supervisor about it? Okay, get going. Okay. If you run into trouble, just write us again. Say, not quite sure, or it's unclear how this is supposed to work. Just get it started. You don't need it for this assignment, but you need to get it started so that when you do need it, it's all in place. Well, that's another thing. So if you get your account before next Thursday, you can sign up for the course officially on the website, and it'll allow, with that Scinet account, it'll allow your submissions. Otherwise, we'd have to do some manual interventions and creating of temporary accounts. So let us know if towards the end, towards next Thursday, or let us know on Tuesday if you don't have this yet. We'll have to set up something temporary for you. Okay, but get it started. If you say I just didn't do it, no. You said my supervisor is on a conference, it's a different story. Okay. Second part, since you're gonna not use Scinet right now, make sure you have a laptop with a GNU C++ compiler, so that's G++, and try and get version 4.7 or higher, so the few C++ 11 specific things that you might use will actually work. Version 5 is out by now, so it shouldn't be too hard to get at least 4.7 for whatever you're using. And then the actual heart of the matter. I'll post this also on the website, but just for completeness in the slides, we're going to write a little C++ program. We're going to create a table. We'll have 3 columns. It'll have an X column, a Y column, and a Z column. X is a set of values from -5 to 5. I think I said 100 of them. And Y is the sign of 2 times that. And Z is supposed to be the cosine of 3, X that. So you have to generate these values and write them out to a file. The file can be called lissajou.txt. Make it plain text. Don't try and make it a fancy table with lines and stuff. Don't bother with that. Spaces to separate the columns is more than enough for this purpose. So you should write some functions, f and g, that do sine 2x and cosine 2x, and call those functions in the main routine. That's the idea of what to write. I know it's simple. We'll just get everybody going with C++ or show that you already know how to code. A few hints, even if you know C++, to what we're looking for. Don't try to hard code values. So there's -5, 5, 2, 3, 100, and these should just be exact. Store those in variables and reuse them. That's just good practice. If you're using variables, give them names that make sense. ABC is not a good name for a variable. Indent your code properly. That's just, it's common sense, but please do it from the start. anytime you start a new code block, indent it 4, 3, 2, 8. How many space you want? Be consistent and have everything in the same block indented the same way. And comment your code. Let us know why you're doing or why you're coding in what you're coding. And in general, that's really why these hints exist. Try to write code that if you saw this code in a year, you would still know what it does. If you can write like that, you've got the basics of good coding. And I don't mean understand it after you looked at it for a week, okay? I mean, read it for 5 minutes and know what it does. Then compile it and submit the code, a text file of what you did, the output, and tell us how you compiled it and how you ran it. Ran should really just be, I typed in this command, but tell us in detail what you did. This is especially useful when things aren't what they're supposed to be, so we know what you might have done wrong. It's probably better just to give it a reasonable name, like what I did.txt, my first program.txt, output.txt. Just, yeah. So we won't prescribe what it's called, but you know. What else? Oh yeah. So you're using this. You're going to use the website to submit this. There's an assignment Dropbox there. The late penalty we went over last time, and everything should be plain text. I don't want any doc files. I don't even want an Excel sheet. I don't even want a rich text format. Plain text is all we want to see. Okay. So don't forget, Wednesdays 2 to 3 we have office hours, but you can email courses at sign@utoronto.ca anytime you want to get more help. And okay, see you next Tuesday.